Tonight, we are going to slow down a process that normally happens too quickly and at a scale too large for anyone to watch directly. One short sentence enters a neural network. The network predicts the final word. Its prediction is wrong. From that small error comes a chain of calculations that reaches back through every layer, changes millions or billions of numbers by tiny amounts, and makes the next prediction slightly different. This repeated loop is what engineers usually mean when they say that a neural network is learning. The word learning can make the machine sound more human than it is. The network does not sit at a desk. It does not feel surprise when the answer is wrong. It does not understand a lesson in the way a person might. During training, an optimization procedure adjusts parameters so that a chosen measure of error tends to become smaller on examples drawn from data. Yet something remarkable can still emerge. Without a programmer assigning a meaning to every internal unit, the network can develop distributed representations that support language, vision, prediction, and control. By the end of this journey, you will understand the forward pass, the loss, the backward pass, gradients, optimizers, batches, regularization, generalization, and the long scale of a modern training run. There is no formula you need to hold in memory. We can follow the error as if it were a quiet amber signal moving through the midnight observatory, leaving very small changes behind it. Whenever you are ready, you can let those changes become distant. Chapter 1. The first wrong word. The sentence is simple. Beyond the observatory window, the night was perfectly blank until a single star began to glow. We remove the final word and ask the network what should come next. Before training, its parameters may have been initialized with random values chosen according to a careful statistical recipe. The network contains structure, but not yet the patterns required for this task. It receives the earlier words and produces a distribution over possible continuations. Perhaps it predicts table, perhaps river, perhaps a common fragment that fits no grammar at all. The correct word, glow, receives very little probability. The first important fact is that the network must produce something before it can be corrected. Learning begins with a prediction. In supervised learning, an example often contains an input and a target. The input is what the model sees. The target defines the answer against which its output will be compared. In language model pre-training, the target can be the next token already present in a sequence. The text supplies both context and continuation. The network is not shown an explanation of why glow fits. It is not told about stars, night, or grammar as explicit symbolic rules. It receives a training signal derived from the mismatch between its predicted distribution and the observed target. One example teaches almost nothing by itself. It is a small pressure. Across enormous collections of examples, pressures accumulate. Some patterns repeat. Words appear in related contexts. Structures that help many predictions become useful to preserve. The machine's knowledge is therefore not stored as a library of complete training sentences. Some fragments may be memorized, especially when they repeat or when the model has enough capacity. But the broader ability comes from parameters shared across many examples. A change made after this sentence can affect predictions for other sentences because the same weights participate in both. Think of a large network of adjustable channels. A signal flows through many routes. No single channel contains the meaning of night. Together, their settings transform one pattern into another. At the start, the roots are poorly tuned. The network's mistake is expected. What matters is whether the training procedure can assign responsibility for that mistake. Which connection should change? By how much? If an early layer changed a little, would the final prediction move toward glow or farther away? The answer depends on everything downstream. This is the problem that backpropagation helps solve. But before the error can travel backward, information must first travel forward. The sentence enters the first layer. Chapter 2: A River of Activations. A neural network is a composition of transformations. The input becomes numbers. In a language model, tokens are mapped to vectors. Position information distinguishes the first word from the fifth. Layers combine and transform these representations. Each stage produces activations, the temporary values created for this particular example. Parameters and activations are different things. Parameters are the learned settings that persist between examples. Activations are the moving signals generated when one input passes through those settings. A weight may remain in memory for the entire training run. An activation may exist only long enough to help calculate an output and its gradient. Imagine water moving through a system of gates. The gate positions are parameters. The pattern of water at one moment is an activation. Training changes the gates so that future flows take more useful paths. The analogy is incomplete because neural calculations include multiplication, addition, normalization, nonlinear functions, attention, and other operations. Yet it captures the distinction between a model's persistent state and the temporary state of a computation. At each layer, a weighted combination is formed. A nonlinear transformation allows the network to represent relationships more complex than one large linear map. In a transformer, attention lets positions exchange information according to learned queries, keys, and values. Feed-forward blocks transform each position further. Residual connections provide paths through which information and gradients can move more easily. Normalization helps control scale. Many design choices exist because deep networks are not automatically easy to train. If signals shrink too much as they pass through layers, useful differences can vanish. If they grow too much, activations can become unstable. Initialization matters because the first forward and backward signals must remain in a workable range. Glorot and Bengio's work on deep feed-forward networks helped clarify how activation functions and initialization affect training. Later architectures developed many additional techniques, but the quiet objective remains: preserve enough signal that each layer can participate in learning. Our sentence moves through the network. Early representations are transformed. Later layers combine broad contextual patterns. At the output, a set of scores is converted into probabilities over possible next tokens. Table is high, river is lower, glow is nearly absent. This entire computation is called the forward pass. It answers the question, with the parameters as they are now, what does the network predict? During inference, a forward pass may be almost all that happens. The model receives an input and produces an output. During training, the forward pass is only the first half of a larger loop. The activations are often retained because the backward calculation will need them. This is one reason training consumes much more memory than merely running a trained model. The system must preserve intermediate information, gradients, optimizer states, and other working data. Now the predicted distribution and the target are present together. The training system needs to convert their difference into one number. That number is called the loss. Chapter 3. Giving error a number. A machine cannot optimize the vague instruction, become better. It needs an objective that can be calculated. For next token prediction, a common loss penalizes the model when it assigns low probability to the token that actually appears. If glow receives a tiny probability, the loss is large. If glow receives a high probability, the loss is smaller. The precise mathematical form is often cross-entropy. For our journey, the essential idea is enough. The output distribution and the target are compared, and the result is a scalar measure of error. The loss compresses a complicated mistake into one number. That compression is useful because optimization requires a direction, but it also defines the boundaries of the lesson. The network is rewarded for reducing the chosen loss. It is not automatically rewarded for truth, fairness, causality, helpfulness, or wisdom unless those properties are represented by data, objectives, constraints, or later training stages. A low loss means success according to the measurement. It does not mean every human goal has been satisfied. This distinction becomes important at scale. A language model trained to predict tokens can acquire broad capabilities because language contains descriptions, arguments, procedures, and patterns about the world. But prediction remains the training objective. The system can learn a fluent statistical structure that occasionally supports false or harmful continuations. Training objectives are lenses. They make some errors visible and leave others dim. Even within the objective, one example is noisy. A rare sentence may produce a large loss. A corrupted example may point in an unhelpful direction. If every single example controlled the model completely, learning would be unstable. So training usually aggregates loss across a batch, a group of examples processed together. The average creates a temporary estimate of how parameters should change. The estimate is not exact for the entire dataset, but it is computationally practical. The loss can be imagined as height on a landscape. Each possible setting of all parameters has a height. Lower regions correspond to smaller loss. This image is useful and misleading at the same time. A real network may have billions of parameters, so its landscape has billions of dimensions. There is no mountain range a person could literally view from above. The surface can contain flat directions, sharp directions, symmetries, saddles, and many connected low-loss regions. The two-dimensional drawings used in explanations are shadows of a much larger object. Still, the landscape metaphor gives us a question. From the current position, which small movement would make the loss decrease most quickly? The answer is encoded in the gradient. To calculate it efficiently, the amber error signal begins to travel backward. Chapter 4. The signal traveling backward. Backpropagation is often described as blame moving through a network. That description is memorable, but the mechanism is calculus. The network is a chain of differentiable operations. The chain rule tells us how a small change in one quantity affects another quantity composed from it. Starting from the loss, automatic differentiation works backward through the recorded computation. It calculates how sensitive the loss is to each parameter. This sensitivity is a derivative. Collected across all parameters, the derivatives form the gradient. Suppose one weight increased by a tiny amount. Would the loss rise or fall? A positive gradient component means one local direction. A negative component means the other. The magnitude indicates local sensitivity, though optimizers may later rescale it. No parameter receives a sentence explaining its role. It receives a number. The output layer is closest to the loss, so its relationship is calculated first. The signal then passes through earlier transformations. At each operation, the backward rule combines the incoming gradient with local information from the forward pass. This is why intermediate activations were preserved. The derivative of an operation often depends on the values that pass through it. By the time the backward pass reaches the first layer, every trainable parameter has an estimate of how changing it would affect this batch's loss. The 1986 paper by David Rumelhart, Jeffrey Hinton, and Ronald Williams described a learning procedure that repeatedly adjusted connection weights to reduce the difference between actual and desired outputs. Its historical importance lies not only in minimizing error, but in allowing hidden units to develop useful internal features rather than requiring every feature to be designed by hand. Backpropagation itself does not decide how large the update should be. It provides gradient information. An optimization algorithm uses that information to move the parameters. The backward signal can encounter difficulties. Gradients may vanish as they pass through many layers, becoming too small to train early components. They may explode, becoming numerically unstable. Operations may have poorly conditioned geometry, so progress is fast in one direction and painfully slow in another. Noise from batches can make the direction fluctuate. Deep learning architectures contain many responses to these problems. Initialization schemes, residual paths, normalization, clipping, carefully chosen activations, and optimizer design. Yet beneath all of them is a simple repeated event. The model predicted table. The target was glow. The backward pass has now translated that mismatch into a gradient for every participating parameter. The network has not changed yet. The optimizer is waiting. Chapter 5. Moving the weights. The simplest gradient update takes a small step opposite the gradient. If the gradient points toward increasing loss, move the other way. The size of the step is controlled by a learning rate. Too small a learning rate can make progress extremely slow. Too large a rate can overshoot useful regions or cause training to diverge. Schedules often change the rate over time, beginning cautiously, rising or holding for a period, and then decreasing as training approaches a more refined state. Stochastic gradient descent uses gradients estimated from batches rather than the entire dataset. Its path is noisy. Instead of descending a smooth hill in one straight line, it trembles through high-dimensional space. The noise is not purely a defect. It can help the trajectory move through the landscape, avoid depending too precisely on one batch, and interact with the geometry of the model in ways that affect generalization. Optimizers add memory to the movement. Momentum accumulates a running direction, smoothing some fluctuations and carrying the update through shallow variations. Adam, introduced by Diederik Kingma and Jimmy Ba, maintains adaptive estimates related to the first and second moments of gradients. In practical terms, it gives parameters different effective step sizes based on the history of their gradients. Adam became widely used because it is efficient and works well in many noisy, large-scale settings. But an optimizer is not a universal guarantee. Deep network objectives are non-convex. The final result depends on architecture, data order, initialization, schedules, precision, regularization, and countless implementation details. For our single sentence, the update is tiny. Some pathways that supported table become slightly less favored. Pathways that could support glow in similar contexts become slightly more favored. The exact interpretation is distributed. We should not imagine one switch labeled correct word. After the update, the same sentence could pass through again. The probability of glow might rise by a small amount. The loss might fall. But repeatedly training on one sentence would create memorization, not broad ability. The model needs diverse examples. Another sentence arrives, then another. Their gradients sometimes agree and sometimes conflict. One example pushes a parameter upward, another pushes it downward. The optimizer integrates these pressures over time. Learning is therefore not a clean storage operation. It is negotiation among many examples through shared parameters. Common patterns receive repeated support. Rare patterns may survive if their signals are strong or represented adequately. Contradictory data can produce compromise, uncertainty, or unstable behavior. Bias in the data can become bias in the parameters. The updated network does not contain a list of all the corrections it received. It contains the result of their interaction. One training step is complete. Forward pass, loss, backward pass, optimizer update. Then the next batch begins. Chapter 6. Learning from small batches. Modern datasets are too large to process completely before every update. Instead, training divides examples into batches. A batch may contain many sequences, images, or other samples. Hardware performs the same kinds of operations across them in parallel, making efficient use of accelerators. The gradient from one batch is an estimate of the gradient over the broader training distribution. A different batch would produce a different estimate. This stochasticity gives training its irregular rhythm. Loss falls overall but may rise from one step to the next. Gradient norms change. Some batches contain easy patterns. Others contain rare formats, long dependencies, or noisy text. Engineers watch moving averages because individual steps are too variable to interpret alone. Batch size affects both computation and learning dynamics. Larger batches produce more stable gradient estimates and can use hardware efficiently, but they require memory and may require different learning rate choices. Smaller batches introduce more noise and more parameter updates for the same number of examples. There is no single ideal batch, size independent of system and objective. Data order also matters. If related examples arrive together, the model may move strongly in one direction before seeing counterexamples. Training systems shuffle, mix sources, control sampling weights, and sometimes organize curricula. For large language models, the word epoch can become less central than token count. An epoch means one pass through a dataset, but enormous mixtures may be sampled, deduplicated, filtered, or repeated in complex ways. Researchers track how many tokens the model has processed and how compute is allocated across them. The scaling law work by Kaplan and colleagues found approximate power law relations between language model loss and model size, dataset size, and compute across studied regimes. Later chinchilla experiments examined compute-optimal allocation and found that, in their setting, model size and training tokens should scale together more closely than several earlier large models had done. The lesson is not one eternal ratio. The lesson is that a training budget can be spent in different ways. More parameters without enough data may leave capacity undertrained. More data without enough model capacity or compute may have diminishing value. Optimization is also an economic design problem. Inside each step, however, the process remains recognizable. A batch enters, activations flow forward, losses are combined, gradients flow back. The optimizer changes parameters, counters advance. This loop may repeat hundreds of thousands or millions of times. To survive that repetition, a deep network needs stability. Chapter 7: Keeping Deep Networks Stable. Training a deep network is partly the art of keeping numbers in useful ranges. If early weights are too large, activations and gradients may grow. If they are too small, signals may disappear. If updates are abrupt, the network can forget useful structure or become numerically unstable. Initialization gives the model its first balance. Different schemes choose parameter scales based on the number of incoming and outgoing connections. The goal is to keep variance from collapsing or exploding as signals cross layers. Normalization provides another form of control. Batch normalization became influential because it enabled faster and more stable training in many architectures. Its original explanation emphasized changes in layer input distributions. Later studies showed that its benefits were more complicated, including smoother optimization behavior and support for larger learning rates. Transformers commonly use layer normalization, which normalizes within a token's features rather than across a batch. Placement before or after blocks affects training behavior. Residual connections allow a layer to learn a change relative to an existing representation instead of rebuilding everything. Gradient clipping limits unusually large gradients. Mixed precision training uses lower precision arithmetic for efficiency while protecting sensitive calculations. Loss scaling prevents small gradients from disappearing in limited numeric formats. Regularization addresses a different instability, fitting the training data too specifically. Dropout randomly omits units and their connections during training. The original method was presented as a way to reduce overfitting and discourage fragile co-adaptation. Weight decay discourages certain large parameter values. Data augmentation presents altered examples that preserve a desired label or structure. Each technique introduces an inductive bias, a preference among solutions that fit the data. The model is encouraged to learn patterns that survive perturbation, sharing, or constraints. But more regularization is not automatically better. Too much can prevent the model from fitting real structure. A technique successful in one architecture may be unnecessary or harmful in another. Training recipes are empirical objects refined through measurement. The network now predicts glow more often in appropriate contexts. Training loss has fallen. That sounds like success. The next question is harder. Will the model perform well on sentences it never saw during training? Chapter 8. Remembering patterns, not examples. Generalization is the reason training matters. A model that only reproduces its training examples is a complicated archive. A useful model applies learned structure to new inputs. To measure this, researchers separate data. Training examples influence parameter updates. Validation examples guide choices such as schedules or checkpoints. Test examples are reserved for final evaluation under a defined protocol. If training loss keeps falling while validation performance worsens, the model may be overfitting. It has become better at the observed sample without becoming better at the broader distribution we care about. The boundary is not always simple in modern systems. Large models can memorize and generalize at the same time. Duplicate or contaminated data can blur evaluation. Performance may improve on familiar distributions and fail under distribution shift. Deep double descent research showed that the relationship among model size, training, and test performance can be less simple than the classical picture of one smooth overfitting curve. In some studied settings, performance worsened near an interpolation threshold and improved again as capacity increased further. This does not mean bigger is always better. It means high-dimensional optimization contains regimes that resist simple intuition. Why do heavily over-parameterized networks generalize at all? There is no single complete answer. Architecture, data structure, optimization path, initialization, regularization, and implicit biases all contribute. Gradient-based training does not select randomly among every solution that fits. Its path favors some representations over others. Generalization is always relative to a distribution and task. A language model may generalize syntax across new sentences and fail on a new factual domain. A vision model may recognize objects under ordinary lighting and fail under a subtle perturbation. A system can perform well on benchmarks while missing a real-world constraint the benchmark never measured. This returns us to the loss. The optimizer can only follow signals available in the objective and data. Human evaluation, safety testing, adversarial analysis, and deployment monitoring exist because training loss is not the whole specification. The model has learned something real when its behavior improves on appropriately held-out cases. But the content of that learning is distributed, statistical, and bounded by experience. Our once wrong sentence is now easy. The network assigns high probability to glow. The more interesting evidence is that it also handles new sentences about stars, light, darkness, and gradual change. One update did not create that ability. The training run did. Chapter 9. From one update to a training run. Step back from the single sentence. Imagine thousands of accelerators arranged in a data center. Parameters are divided or replicated across devices. Batches move through parallel pipelines. Partial gradients are communicated and combined. Checkpoints preserve the model's state in case hardware fails or training becomes unstable. The conceptual loop is unchanged, but engineering surrounds it. Data must be loaded quickly enough to keep expensive processors busy. Communication must not become the bottleneck. Numeric precision must balance speed, memory, and stability. Metrics must reveal divergence before a long run wastes its budget. Researchers run smaller experiments to choose recipes. They inspect loss curves, gradient norms, validation results, throughput, and hardware health. A model can fail because of mathematics, data, software, networking, cooling, or one corrupted state. At this scale, learning is a coordinated physical process. Electric current changes transistor states. Memory devices hold parameters and activations. Networks transmit gradients. Cooling systems remove heat. The abstract descent through a loss landscape is implemented by machinery in buildings connected to power and water systems. After many steps, training reaches a stopping point. Perhaps the compute budget is exhausted. Perhaps validation improvement has slowed. Perhaps the scheduled number of tokens has been processed. The final checkpoint is not necessarily the last one. Teams may choose an earlier checkpoint with better evaluation behavior. Later stages may fine-tune the model on curated examples, human preferences, tool use, safety policies, or specialized tasks. The parameters produced by pre-training become the starting point for more learning. Even then, we should keep the central distinction clear. The network has optimized behavior under objectives. It has not been handed a list of explicit beliefs. It may encode useful concepts without representing them as a human would. It may produce an explanation of gradient descent without possessing introspective access to its own training history. So what happens inside AI while it learns? An input becomes activations. Activations become a prediction. The prediction and target become a loss. The loss becomes gradients. The optimizer turns gradients into small parameter changes. Batches make the signal stochastic. Architecture and normalization keep it stable. Regularization and data structure influence which patterns survive. Evaluation asks whether those patterns generalize. Then the cycle repeats. There is no single moment when understanding switches on. There are many small updates, each local in calculation but shared across future behavior. In the midnight observatory, context releases the final amber gradient. It travels back through the quiet network and fades. The weights settle into values almost indistinguishable from the previous step. The next sentence arrives. Before it does, we can pause over one final detail. No single weight contains the lesson. A parameter in an early layer does not store a readable rule such as choose this word after that phrase. Its contribution is smaller and more distributed. It may alter the sensitivity of one intermediate feature, which slightly changes several later activations, which in turn shifts a broad field of possible outputs. The useful behavior belongs to the arrangement, not to one isolated number. This is why inspecting a trained network can be so difficult. We can record every weight and every activation. We can calculate exactly how the update was produced. Yet the human explanation of what the network learned may remain incomplete. The mechanism is visible as mathematics, while its internal representation is spread across many interacting dimensions. The batch also leaves no neat boundary around itself. One example may pull the parameters gently in one direction, while another pulls them elsewhere. The update is a negotiated motion through a crowded landscape. Some directions reinforce one another. Some cancel. Some matter only because an earlier update changed the slope that the next example will encounter. Over thousands of steps, these tiny negotiations form a path. The path is not usually the shortest imaginable route, and another training run can reach a different region even with the same architecture and data. Random initialization, batch order, numerical precision, and optimization settings all influence the journey. Two networks can therefore learn similarly useful behavior without ending with identical internal coordinates. Generalization appears when that path captures regularities that extend beyond the examples already seen. The network is not rewarded merely for remembering a training sentence. It is useful only when the same distributed structure helps on a new sentence, image, sound, or situation. Validation data provides a quiet window onto that distinction. Training loss may continue to fall while validation behavior stops improving, revealing that the model is becoming more faithful to its sample than to the wider pattern the sample was meant to represent. And scale does not remove these questions. More parameters can provide room for richer representations. More data can expose a wider range of structure. More compute can support more updates. But each resource must meet the others in a reasonable proportion. A very large model trained on too little varied data may not use its capacity well. A vast dataset paired with too little optimization may remain only partly absorbed. Training is therefore not one dial-marked intelligence. It is a coordinated system of model, objective, data, computation, and evaluation. Context watches the final gradients cross the observatory floor like dim lines of rain. None of them is dramatic. Together, they explain how a machine can change without being explicitly rewritten after every mistake. The model is still imperfect. The objective is still incomplete. The data is still a sample of a larger world. But one prediction has become slightly less wrong. For tonight, that is enough. The activations can dim. The batches can stop at the edge of the next update, and the long river of gradients can become silent until morning. Nothing inside the network needs to hurry now. The next forward pass can wait. The next error can remain unmeasured. And the next small correction can rest beyond the darkened edge of the observatory. Learning will resume as it always does. One example, one signal, and one almost invisible change at a time.